Hey everyone, and welcome. Today we're jumping into a really essential skill in calculus, how to evaluate limits analytically. We're going to move past just looking at graphs and making guesses, and instead we're going to build a solid problem-solving toolkit. Seriously, by the end of this you'll have a clear step-by-step strategy to knock out limit problems with total confidence.
All right, so here's our game plan. We're going to kick things off with the easiest kind of limit there is. Then we'll face the one big problem that trips everybody up. From there, we'll build out our algebraic toolkit to handle it, learn about a pretty clever theorem for those tricky special cases, and then, finally, we'll wrap it all up into one clear, easy-to-follow strategy.
First up, let's talk about the most straightforward tool in our entire kit. You know, sometimes the answer is staring you right in the face, and it all starts with a simple idea called direct substitution.
So for a lot of functions, the ones we call well-behaved because they're continuous with no weird breaks or holes, finding the limit is about as easy as it gets. This is what we mean by direct substitution. You literally just take the number that x is approaching and plug it straight into the function. That's it.
And the best part, this simple trick works for a huge range of functions you see all the time. Got a polynomial? Just plug in the number. A rational function, a fraction, as long as the denominator isn't zero? Yep, just plug it in. Basic trig functions like sine and cosine, you got it. Just substitute the value. This is always your first, best, and easiest move. Of course, direct substitution is fantastic, right up until it isn't. And that brings us to the real heart of the matter, the central problem we need to solve. What in the world do you do when the easy way just doesn't work?
This right here is the big one. You do everything right. You plug in your number, and the top of your fraction becomes 0, and the bottom becomes 0 too. Now, your calculator will just throw up its hands and give you an error. But in calculus, this is something else entirely. It's a clue.
So, take a look at this example. When we try to find the limit as x heads towards -3, plugging it in gives us 0 divided by 0. This has a special name. It's called an indeterminate form, and trust me, it's the most common roadblock you're going to hit.
Now this is absolutely crucial. Getting 0 over 0 is not a dead end. It doesn't mean the answer is 0 or 1 or that the limit is undefined. Think of it more like a big flashing sign. It's the problem telling you, hey, time to open up that toolkit and do a little more digging. In fact, this is where calculus really starts to get interesting.
Okay, so what's in that toolkit? Well, for most of these 0 over 0 problems, your solution is going to come from one of two really powerful algebraic techniques. Let's crack them open and see how they work. Our very first tool is called the cancellation technique. Look, if you've got a fraction and you're getting 0 on the top and the bottom, there's a good chance it's because they share a common factor. So your job is to find that factor, cancel it out, and then try plugging the number in again on the new, simpler function. And here's the really cool part, the reason this whole trick works. The original function and the one you get after canceling are identical everywhere, except for one tiny little hole right at the point you care about. And since the limit only cares about what's happening near the point, not at the point, finding the limit of the simplified function gives you the answer. You've basically just filled in a mathematical pothole.
All right, tool number 2 is what you pull out when you see square roots, or radicals. If you get 0 over 0 here, the secret move is to rationalize. You multiply the top and the bottom by something called the conjugate, which is just the same expression with the sign in the middle flipped. It sounds complicated, but this one clever trick magically creates a common factor that you can then cancel, clearing the way for direct substitution to finally work. But what happens when plain old algebra isn't enough? For some really tricky functions, especially ones involving trig, we need something a little more elegant, a more conceptual tool. And that's when we pull out our ace in the hole, the squeeze theorem.
You know, the idea behind this is actually super intuitive. Just imagine your function, let's call it f of x, is always trapped or squeezed between two other functions. Now, if you know for a fact that the function on top and the function on the bottom are both heading to the exact same point, well, what choice does the function in the middle have? It has no choice. It has to get squeezed into that same point too. And this right here is just the fancy math way of saying exactly what we just saw in that picture. It says if your function is squished between two other functions, and those two outer functions are both heading towards the same limit, L, then your function in the middle must also be heading to L. Simple as that.
So why is this so important? Well, it's the key that unlocks some really fundamental limits in calculus that algebra just can't touch. The most famous one is proving that the limit of sine of x divided by x as x gets closer and closer to 0 is exactly 1. The squeeze theorem is pretty much the hero of that story.
Okay, we have covered a ton of ground, and we've added some seriously powerful tools to our kit. So now, let's put it all together. Let's build a simple, repeatable game plan that you can use for pretty much any limit problem that comes your way.
Here it is, your 3-step strategy. Step 1, always, and I mean always, try direct substitution first. If you get a nice normal number, great, you're done, high five. Step 2, if and only if you get 0 over 0, it's time to open that algebraic toolkit. Try factoring or try rationalizing. And step 3, if algebra is still not working, don't forget you have that ace up your sleeve. Start thinking about the squeeze theorem, especially if you see trig functions.
If you follow this strategy, you're going to be able to tackle a huge variety of limit problems. But more than that, you've just unlocked the next giant idea in calculus. Because these exact tools we just built, they are the engine that allows us to find the slope of a curve at one single precise instant. And that, my friends, is the derivative. That's where we're headed next.